to the best of our knowledge, this is the first time when this flocking optimization, drone flocking optimization problem has been solved using multi-objective optimization, and we are representing all possible solutions. Means these are the just 12 decision variables, and these are the 6 fitness function, and this is the class diagram of our simulator, where we have the 5 classes, one solutions, particle, boats. These are the drones with no coordination, only the movement, and the co-boat is with the coordinating boats, and then the environment is the environment where they are flying. So it's a confined environment, and then we have applied one optimizer, that is NSGA-II here. I just want to quickly share this simulation that we obtained from our MOFlock simulator. So here we have the 30 drones, and the speed of flight is 8 times we just created. And quickly I want to tell you that out of these 6 objectives, we converted to them 2 objectives, F1 and F2. This F1 contains these 2 objectives and F2 contains these 4 objectives. Actually, these 4 objectives says that if they are into one class, it means they are if they are not opposite objectives. Means if correlation increases, then the collision will not increase, collision will decrease. Correlation increases means collision will also be maintained. Here we have taken since it is a multi-objective optimization problem, so in the Pareto front, we have taken 2 extreme points where the blue dot, these blue drones are given the full weight to the F1. They have the highest weight to the F1, means for this collision wall avoidance and the speed. They want to make high speed and avoid the wall, while the red one are not respecting the wall boundaries and are not respecting the speed also. For them, these 4 things are more important. And when they fly, you can see that since for the red, there may be the situations, and that is why this multi-objective optimization, this Pareto front is giving us the options, that if you are using it for military purpose, if you are using it for the delivery purpose, if you are using it for the search purpose, you can slide that how much weight you want to give to F1 and how much weight you want to give to F2. So you have a class of solutions. Here for this. In this simulation, we have given F1 2 extreme points. In the Pareto front, we have taken 2 extreme points and simulated those. So you can see that these red are not respecting the walls. For them, the wall is not important, right? For blue, the wall is important. So if you see the flocking, so the red are crossing the boundaries, these GPS walls, they are crossing the boundaries, but the blues are not crossing the boundaries. While for the blues, coordination is not important. For the reds, the coordination is important. They are more collaborative, making more coordination. So there may be certain situations in the real world, and therefore we here, by this optimization, solving this optimization problem, we are giving the options to the user that whatever kind of application you have, you can select, you can choose the algorithm. You can choose the algorithm parameter, optimized algorithm parameters. You can see here the blue are not coordinating very nicely, while the red ones are coordinating nicely. If you want to make the compromise with the both, means if you want the properties of both, you can take some solution in between also, and so on. Okay, here this is sorry, just a second. Yeah, here this another video where we have implemented the target tracking. If you want to reach a particular target, some based on some computer vision algorithm, if you want to target something, in that case, you can see here the same, the red and blue, the same, but here the roles are changed. Actually, now the red are respecting the boundary and blue are not respecting the boundary. And look here, the target is changed, then they changed and they are tracking the target in dynamic environment. Even if the target is dynamic, they are changing their target. So I know the time is, this is the dimensional reduction we have done using the PCA to convert the 6 objectives to the 2 objectives. Just here, it's a discussion about that they are which objectives are not contradictory to each other. And here are the 2 extreme points. You can see here this A, and here is the B point. So here this A has the highest priority to F1 and B has the highest priority to F2. So one can use any point in between and can decide that how much priority he want to give to F1 and F2. And these are the optimal parameters we got for point A and point B. Okay, so just here it is discussed that for point A, if you can develop some kind of drones which can collide with each other, the collision is allowed, right? But you want a speed, but the collision is allowed, then in that case, better you go with this solution, point A solution. And these kind of drones are existing. I put this picture of the drone in which the collision is allowed. It is taken from the internet. So this kind of drones can collide with each other. Okay, so that's all from my side. I say that there are much research is possible in this case. Other kind of optimizers can be used instead of the NSGA-II. We can find better optimizer who can solve the problem in most efficiently, so that more calculation can be done in minimum possible time, and therefore the delay can be minimized. Reinforcement learning can be used for similar kind of algorithms. So that's all from my side. Thank you so much. I'm okay to take the questions now. I hope I finished in time. Professor Kim.
Bansal, it was very interesting. The first time I saw the drone swarm was in 2018 Winter Olympic, which was held in Pyeongchang, South Korea. In the opening ceremony, I saw many drone swarm and flying with the lights and formating 5 circles, Olympic circles like that. So it was very interesting. And since we don't have enough time, I will ask one question. One question is, okay, you mentioned about the drone swarm flocking optimization using NSGA-II. And then what are the other main research areas in the drone swarm where some intelligence-based evolutionary algorithm may be applied?
Professor Kim, this is really a good question, and I thank you. This is the one problem that we solved using the drone. Just a second. I think, can I stop sharing so that this is the one problem of drone flocking optimization that we solved here. But it is not only the coordination during the flocking is required, but the navigation, how to reach navigation. During the navigation also the optimization is required, that how to navigate from one point, from base to the target location in the minimum possible time by finding the minimum shortest path. So in the real time, they can do the calculation. All the drones can help each other and can find the shortest path. This is another optimization problem which is required to be solved in case of the drone swarm optimization. Simultaneously, another problem is this interagent distance. This interagent distance, this dispersion and aggregation is the one most important challenge for the drone swarm, that how to find the optimal distance between 2 drones, minimum and maximum distance between 2 drones, so that the communication is maintained and the collision is avoided simultaneously. So there are these other challenges related to optimization problems where we can apply the swarm intelligence based algorithms to the drone swarm.
Okay, thank you very much. We have received one more question in chatting window, but since we don't have time, so I think we have to close this session. I thank you very much.
That's not a problem. I'll write the answer. If it is saved, then I'll write the answer via email. So, or the audience can drop an email to me and I'll answer there.
Okay, that's very nice of you. Thank you.
Thank you so much. Thank you so much, Professor. Thank you. Thank you, everyone.
Professor Chung.